Yeah, any questions or comments, guys, before we begin? I'm gonna stop that camera feed. I was actually doing someone's review and I visited their class. So what they did, they had a whiteboard in the background, and just like a typical classroom, they solved problems on the whiteboard while standing, and everyone can just look at everything very clearly. It was really cool. It was like being inside a classroom. But standing up for hours a day, I don't know, while you could sit. Yeah, on Zoom. I'll be on campus next semester, thankfully. I'll be in a classroom. I'm done with Zoom, guys. It wasn't hard to see the whiteboard. It was very clear. It was just like being in a classroom. But yeah, I don't know. This Zoom experience has not been good for students, for my students at least. I don't get to see you guys. You guys don't get to see me. You know, being in a classroom is the best as a student. Okay, so talking about parametric graphs and rates of change. Okay, so we're talking about the derivative here of y with respect to x. So let's talk about this last thing that I was talking about. When there is, let's say, a particle moving in space, in the two-dimensional space. Okay, so this is x and y, and again, there is no t that can be graphed. Let's say this is the movement of the particle. Okay, going this way, let's say. There is movement in two directions. Okay, we have movements. Of course, we have two space variables, x and y. So you're in two dimensions. You can go north, south, east, west, or you can go in any combinations of the two directions. You can go northeast, northwest at some angle or so on. Okay, so here we have, let's say the particles, here is the particle moving on that path. I hope you can see that. Okay, we have movement this way. Okay, that's the movement in the I'm drawing a vector here, okay, I guess, but we have movement in that direction and we have movement in that direction. The particle is going what? North, northeast, north, east. See that? North, east. Okay, now how fast the particle goes in the direction of x is dx dt. Okay, so when we say how fast, it's with respect to time. It's a time derivative. Okay, and how fast the particle moves in the direction of y is dy dt. Okay, these are time derivatives of x and y. Okay, and they have nothing to do with the slope of the tangent line. Nothing to do with that. All right, so to find the slope of the tangent line, this is the, let's say this is the tangent line. All right, the slope of that is dy dx. I hope you guys can see the difference between those derivatives. Okay, this is change in x as time changes. Let's say t is time. This is change in y as time changes, but this is change in y as x changes. Okay, this is your rise over run, gives you the slope of the tangent line. And we said that if we have a parametric function, we have parametric functions, x and y, functions of time or t. If you want to find dy dx, you take dy dt divided by dx dt. And that's kind of obvious because if you were to divide these, the dt's cancel out and you get dy over dx. And here, dx dt can't be 0. And the curve has to be smooth. Okay, we want the derivative to exist. Just a notation, a cool notation that I want to discuss here quickly. All right, so as we know, dy dx in short is just y prime. We know that from calculus 1. Okay, y prime is derivative of y with respect to x. Okay, now derivative of x with respect to t and derivative of y with respect to t, we don't call those prime. All right, so for example, dy dt, I cannot call that y prime because that is confusing, because y prime is reserved for dy dx. So some books use y dot with a dot on the top. And if you want, you could do that. You could do a dot. Dot means time derivative or derivative with respect to the parameter. And of course, dx dt for short, you can write that as x dot if you feel lazy. Okay, so here we have y prime. According to the formula that we just wrote down, y prime is equal to dy dt. dy dt is again y dot over dx dt, which is x dot. Our book doesn't use that notation, by the way. Okay, so let's do an example. Let's go on the next page. Let's say we have a parametric curve. C is defined by x equal to 2t and y equal to t squared minus 1. All right, you could graph that if you want. The book doesn't do anything, Nicholas. The book just, they use dx dt dy dt. They don't use a short notation. Yeah, and here we want to find the equation of the tangent line to see when, I'm not saying at, okay? When you say at implies at some position. When means at some time, when t is equal to 1. Because the independent variable here is the parameter t. All right, so let's see the solution. Okay, slope of the tangent line is dy dx. Okay, again, dy dt doesn't give you slope of tangent line. That's the change in y with respect to t. It's not change in y with respect to x. So what you want to do here is first calculate dx dt, which is equal to 2, and dy dt, which is 2t. Again, if you want to use the dot notation, you're more than welcome. All right, and here slope of the tangent line. Okay, so since we want to find the equation of the tangent line. I need its slope. Okay, and the slope is again dy dx, which you take dy dt over dx dt. Okay, we found those t derivatives. We have 2t over 2, and the slope is equal to 2. All right, slope here is constant. Yeah, that's what's happening. This interestingly has a constant slope. Oh, right, 2t, sorry about that. What am I saying? The slope can't be constant. This is just t. I don't know what I'm thinking. I cancel t in my head for some reason. Yeah, and I said slope is constant. There is no way slope can be constant because this is a parabola. If you plug 2t here for, or 2x over 2 into t, you get a parabola. That's the relation between x and y. So slope here is t. Now, we are finding the slope when t is equal to 1. So you have to evaluate the slope at that time. Okay, this is the slope for any time. And this is the slope for when t is equal to 1. You take dy dx and evaluate. That bar is the evaluation bar. Evaluate when t is equal to 1. Okay, so you just take t and you plug 1 in it, and that just gives you 1. All right, so at the moment when t is equal to 1, rise over run is gonna be 1. Okay, now we have the slope, that's our m. Now to find the equation of the line, you also need the point. That's the point of tangent C. Okay, so again, we need slope, and we need the point of tangent C when t is equal to 1. Can anybody tell me how to find that point, guys?
Would you just plug 1 into the dy dx?
Plugging 1 into dy dx gives us slope. I need the actual point xy.
Plug it into y.
Yes, plug it into xy. Point is x comma y. Okay, I need my x. X is determined by this equation, and y is determined by this equation. All right, so plug 1 into t for x and y. You're evaluating x at, or x of 1. That reads as x of 1 or x at 1. Plug 1 into t here. Okay, so at the moment when t is 1, x is going to be 2. Likewise, y at 1 is plug 1 here. You got 1 squared minus 1, and that's equal to 0. Okay, so here the point of tangent C is 2 for x, 1 for y. So this means that at the moment when t is equal to 1, if this is motion, the particle is at 0.21.
What do you
Okay,
mean 2, 0?
2, 0. Yes, indeed. Let me fix that. Yeah, we have our point, we have the slope, and now we can find equation of the line. You can use any form of the equation. I can use a point slope form, y minus y1 equal to m times x minus x1. This is all calculus 1. Y here is 0, so y minus 0 is equal to m, which is 1 times x minus 2. Okay, so the slope intercept of the tangent line is y equal to x minus 2. All right. So what this means that if you draw the parametric curve and the tangent line at the point 2, 0, its equation is y equal to x minus 2. Okay, you could try it out. Eliminate the parameter if you want. There is another way. Of course, you can. You could try to eliminate the parameter here, guys. I don't suggest you do that. Eliminate the parameter, meaning that you could solve this for t. So t would be x over 2. Okay, plug that in there, and then you could take the derivative, find y prime, and go from there. Okay. Again, I don't suggest that because sometimes it's not easy to eliminate the parameter. So that's the first derivative, which is used for, of course, analyzing how fast y changes as x changes. It tells you when the curve is increasing, when it's decreasing, and so on. You know, anything that has to do with the first derivative. Now the question is, how do we find the second derivative? Because second derivative is used for concavity analysis to determine when the graph is concave up or concave down. So let's discuss the second derivative. Could be a little tricky. And I would say at least 20%, 25% of students on the final mess this up. Okay, again, this is one of those things that I can bet on. Again, I don't want you to be one of those people. All right, so people might say, since first derivative is dy dx over, first derivative is dy over dt divided by dx over dt, then the second derivative is d squared y over dx squared dt squared over dx squared over dt squared. Take the second derivative of each parametric equation and divide, and that would be wrong. Okay, yeah, so let me write it down here. The second derivative, we call that d squared y over dx squared, or y double prime. If you say this is equal to the second derivative of y with respect to t over second derivative of x with respect to t, this would be wrong. This is totally wrong. It's not going to give you, this is not going to give you y double prime, because what happens is that if you, let's say, cancel these dt squares, you get d squared y over d squared x, which is total nonsense. We want d squared y over dx squared. Okay. Yep. So let's see how to find the second derivative. Here, y double prime, guys, make sure you're paying attention. Y double prime is the derivative of the first derivative. Okay, you have dy dx, which is y prime. Then you're taking the derivative of that with respect to x. Okay, not t, with respect to x. So again, this is the derivative of y prime. All right, and let me actually erase that, or maybe move that somewhere else for now. Okay, and remember that the first derivative y prime that we found earlier, or dy dx, this was dy over dt over dx dt. Okay, so this is what we discussed earlier. All right, this is dy dx. Now, if you are finding dy prime, you could write that as dy prime over dx. Okay, that's what the second derivative is, dy prime over dx. If you want to find this, then all you have to do is take this formula and replace y with y prime. Let me write that y in blue. Okay, so this is equal to dy prime dt divided by dx dt. All right, this is the formula for second derivative of y with respect to x. As you see, we do not have the second derivative with respect to t here. You're taking the first derivative of y prime with respect to t, dividing that by dx dt. All right, so let me show you an example. I strongly suggest that you do not memorize these formulas. You memorize, you're almost guaranteed to make a mistake on the test or in your homework. Make sure you do enough practice. So let's say we have this parametric curve. Let's say here x is e to the negative t, and y is e to the 2t. And here we want to find y double prime. Again, this tells us about how fast the slope of the tangent line increases or decreases. How fast the slope of the tangent line. So imagine we have some curve, okay? And you're moving along this path, let's say. Okay, so we want to know how fast the slope of these tangent lines change. Okay? How fast those derivatives change. All right, so what you have to do here is find, first of all, dx dt and dy dt as before. Dx dt is negative e to the negative t. Dy dt is 2 e to the 2t chain rule both. Okay, yeah. We want the second derivative. To find the second derivative, we of course need the first derivative. So find the first derivative first, okay? That would be dy dx. Again, I'm not gonna memorize anything. What makes sense is that dy dx is just the ratio of these two, because when you divide those, dt's cancel out and you get dy dx. So we take dy over dt, divide that by dx over dt. Again, look at that. Those dt's cancel, you get dy over dx. You found those time derivatives, divide them out. We have 2e to the 2t divided by negative e to the negative t. All right, so before you do anything else, please simplify. Here you can move e to the negative t up to the exponent and combine e to the 2t with e to the t, you get negative 2e to the 3t. Okay, so again, this gives us slope of the tangent line. It gives us a rise over run at some point. All right. Now we want, so again, this is y prime. Now we want y double prime. So again, I haven't, let's assume I haven't memorized anything. Okay, derive these formulas on your own every time, guys. That's my strong advice. Do not look at the formulas. It's not gonna help you. Derive the formula every time. Okay, so again, let me use a color here. So let's say here the dependent variable is in blue. Y double prime is the same as this, but you're replacing y with y prime. That's dy prime over dx. Okay, if this was y triple prime, then you're doing dy double prime over dx. You're taking the derivative of the second derivative in that case. Okay, so dy prime over dx, again by chain rule, you take dy prime dt, okay, and you divide that by dx dt, right? You take the previous formula and you simply substitute y prime for y. All right, yeah, again, these dt's cancel out. If you go backwards, you get dy prime over dx, which is exactly what you want. All right, so the good thing is that we already have dx dt in the denominator. Dx dt is right there. I have that already. All right, so let me substitute that first. That's negative e to the negative t. Okay, always write down what you already have. Okay, again, dx dt is right there. Put that in the denominator. And on the top, we have to calculate this thing. That's dy prime dt. Dy prime dt is the derivative with respect to t of y prime. And we have y prime from the previous step. Y prime is negative 2e to the 3t. Okay, so I hope you can see that. Yeah, I'm finding the derivative of y prime, and y prime is right there. That's your y prime. Okay, yeah, so what you need to do now is evaluate this derivative, and then you're gonna divide and you'll be done. All right, so on the top we have chain rule again. The derivative of that thing is negative 2. e to the 3t. By chain rule, you multiply by the derivative of 3t, which is 3, and divide that by negative e to the negative t. Okay, so again, when you combine, here you get the negatives canceling out. We have 6 e to the 4t. Okay, so again, what I did is I moved that up. I made the exponent negative. I combined it with that, adding the exponent. 2 times 3 is 6. And again, those negatives cancel out. So this gives us again y double prime, second derivative. Questions?
Professor,
Yeah.
doesn't the denominator become positive when you take the derivative?
Which denominator? This denominator?
Yeah, the negative e to the negative t.
Oh yeah, dx dt is right there. I've already calculated dx dt.
Oh, and we're not taking the derivative of the bottom, only the top, right?
Right, yeah, dx, just taking the derivative of y prime on the top, and then you're dividing that by the first derivative of x with respect to t,
Okay.
which I already
Thank
calculated.
you.
So again, guys, derive the formulas every time. Number one. Second, trust the formulas. All right. Dx dt is right there. We already have it. Yeah, that goes down right there. We do this problem over again, like twice at least, twice or 3 times. Okay, repetition. That's how you learn, repeating. Okay, great. So let's see how much time we have. All right, so here's what we're gonna do. We're gonna sketch a curve, a parametric curve. This is gonna be a really cool kind of curve, okay? And we're gonna do it using calculus because we've established everything we need to understand motion and position when we talk about a parametric motion or a parametric curve. And then tomorrow we're gonna do arc length. Okay, so this is gonna be a long but fun example, okay? Let's say we have a parametric curve defined by x equal to t squared, and y is t cubed minus 3t. And by the way, the book does this problem. They do the problem without certain steps, okay, which is really confusing. I find it confusing. So for example, there are some curves that intersect. Okay, we have sometimes intersection. The question, how do you find that point of intersection? All right, so first of all, good luck eliminating the parameter here. Okay, you can eliminate the parameter if you want, but then trying to recognize that curve is not gonna be easy, okay? It's just better that we leave it in parametric form. And here t again could be any real number. I'm not restricting that. So part A of the problem, I might put this question on the next test or the final. I will put it on either one of those exams. Since it's a long question, I might put it on the final because it could just take about 20 minutes to solve this problem. But it has everything in it, everything, okay? It has the the first derivative part, it has, well, we'll see. We'll see. So part A, you're asked to determine, finally, if C is simple. Remember that a simple curve is a curve that never intersects itself. It's a one-to-one curve, okay? If not simple, then find the point of intersection. And guys, you really, really want to learn this because this is nowhere to be found in the book. I'm not sure if you can find the procedure online, but none of the calculus books discuss finding the point of intersection. None, okay? So remember that a self-intersecting curve, what happens is that for two different t values, you get the same x and same y. That's what it meant. Let's go back to that definition. I think I have it in the previous section. Yeah, so again, for two different t values, we get the same x, same y. That would give you the point of intersection. And that's exactly what we are going to do. So remember that, I'm just going to write this down. C intersects itself if for T1, we'll just call that U. If you don't want to use U, you can just use T1, but I don't want to deal with those subscript. Let's say this U is less than V. First time value is less than the second time value. Of course, if U is less than V, then U and V are not equal. We get X at U equal to X at V. That gives us one equation, and Y at U is equal to Y at V. This gives us a second equation. Okay, we have two equations and two unknowns. U and V are two unknowns. Okay, so let's set up this equation. Let's call that equation number 1. X at U, just take your X function and plug U in it. That's what X of U is. It's U squared. That's equal to X of V, take V and plug it into your X function, so that's equal to V squared. Again, this is X at V. Okay, so our first equation is U squared equal to V squared. Okay, we are establishing this equation. And then the second equation, do the same thing, but for y's. Okay, y at U. This is your y equation, plug U into its t. You get U cubed minus 3U. We want that to equal to y at V, plug V into your y equation. Okay, so this is the second equation. This equation. Okay? Yeah. We have again that equation and we have this equation here. System of two equations, two unknowns. Okay, it's fairly simple to solve the system. This is not a linear system, by the way. You have a quadratic, but again, it's fairly easy to solve the system. So take the first equation. which again says u is equal to v squared. I don't know why that happens here. Okay. All you have to do here is take the square root. You can move the v squared over and factor it out, or you can just take the square root to get rid of those squares. Very simple, as I said. Okay, do square root of the left hand and the square root of the right hand. And that is gonna give you absolute value of u equal to absolute value of v. Okay, you get a plus or a minus. Remember quadratic? When you take square root, you get a plus or minus. So we get u equal to plus or minus a v. U equal to v and u equal to negative v both satisfy this equation. Square both, you're going to get them equal. Okay. Now, my question for you guys is that which one are we going to take? Are we going to take u equal to v or u equal to negative v as our solution? Which one? Should this be true or should u equal negative v?
U equals V.
Say what?
U equals V.
Okay, all right. If I take u equal to v, that would be a contradiction to something that we earlier assumed. No, okay, so guys.
Oh,
here
it's negative because we got the U less than V.
yes, yes. Ahmed, here t is any real number. Here t doesn't have to be time. No, t that we are doing math. You know, in math, t doesn't have to be time always. It could be any real number here. We have to take u equal negative v because we assumed earlier that u is less than v, guys. If you take u equal to v, well, those are the same t values. We're not interested in that. We want to know if for two different t values, we get the same point. Okay, this is what we assume. So we got to go with that assumption. So since we assumed u less than v, then we take u equal to negative v. All right. So whatever v is, u is going to be the negative of that, which makes sense because u is less than v. All right. Now, what you do is you take this equation and you substitute that into the second equation. And that is going to eliminate one of the variables. So substitute into 2. Okay, u is negative v. Every time here you see a u, make that a negative v. Let me write this down. So second equation is u cubed minus 3u equal to v cubed minus 3v, and this becomes negative v cubed minus 3v, 3 times negative v, equal to v cubed minus 3v. Replace u with negative v. Okay, and there you have one equation, and the only unknown here is v, so you can easily solve this equation. Let's cube that. When we cube those negatives, negative v cubed is the negative of v cubed. Yeah, question?
It'll be plus 3V.
Why?
Negative 3 times negative.
Yeah, I'm doing that in the next step. Yes.
Oh, okay, sorry.
Yeah. This step is just me substituting negative v for u. Okay, so here negative of v cubed, negative v cubed becomes negative of v cubed because a negative cubed is negative, and here negative and negative is positive. That's equal to v cubed minus 3v. Okay, one unknown. So what you do with this equation, this is a nonlinear cubic equation. You have to move everything over to one side and set equal to 0. Okay. Yeah, so move everything over, you get 0 equal to 2v cubed, right? When you add v cubed, and then subtract a 3v, you get minus 6v. Okay, now you can factor this out. Factor it out. You get 2v, I could factor that out. That leaves us with v squared minus 3, just minus 3. Okay, now notice, guys, that you cannot divide an equation by its unknown. Some people divide the equation by v. They say, I have a v in common, let me just get rid of it. You can't do that. That will eliminate a solution. All right, now set each factor equal to 0. Basically, we were doing algebra. So we get 2v equal to 0. Okay. And when you set the second factor equal to 0, v squared minus 3 equal to 0, you can now move that 3 over and take the square root. That gives us v equal to positive or negative of root 3. Okay, so we have 3 solutions. Okay, we have v equal to 0 from this equation. V equal to 0. Now, one of these solutions is going to be true. Let's see which. All right. If from this equation v is equal to 0, then we know that our u has to also be 0. Okay, we are solving for u and v. Here u is the negative of 0, which means u is going to be 0. My question for you guys now, can v0 and u0 be the solution?
No, because then we
Yes.
assume one was less than the other.
Yes, we do not. We are not interested in the same t values. We want to know if there exist 2 different t values. So when they're both 0, then it's the same t value corresponding to the same point. That's not what we want. We are assuming u is less than v. Okay. Yeah. So here, but u is less than v. So just ignore this solution. Okay, forget about it. Next one, we have v equal to negative root 3. Okay, from here, positive and negative root 3. Let's see what happens when v is equal to negative root 3. If v is negative root 3, then u is negative v. So negative of negative root 3. Again, I'm using this here to find my v, to find my u, which gives us u equal to positive root 3. So can v equal to negative root 3 and u equal to root 3 be the solution? Again, we are saying what? U is less than v. U is less than v.
No. No.
Right. Yeah. V is negative root 3, u is positive root 3. Here, actually, v is less than u. So you could ignore that also. And the last option is v equal to root 3. If v is root 3, then since we've already determined that u is negative v, u has to be negative above root 3, which is what we want, okay? Satisfies u less than v. Okay, so what happened here is that we found two different t values that give us the same x and same y. So here, C is not simple, okay? We were able to find two such t values. All right, so here we say, therefore, C intersects itself. Okay, when T1 is negative root 3 at T1 of negative root 3 and T2 of positive root 3. Okay, and if you want to find the point of intersection, the point of self-intersection, just plug one of those into your parametric functions, and that gives you the point of intersection. Yeah, I'll just plug either into x and y to get the point of intersection. It doesn't matter which one you plug in. You can plug negative root 3 or root 3 into your parametric functions. Okay, it doesn't matter which one you pick because at both of those, for both of you, those, you get the same x and same y. That's what so let's just plug in root 3 in there. It's easier. Here, x at root 3 or x of root 3, x is t squared. That's root 3 squared, and that gives us 3. Okay, and here y at root 3. Plug that into your, here, let me copy down the parametric. I'll just copy down our parametric equations so you don't have to go back and forth. Yeah, so y at root 3 is root 3 cubed minus 3 root 3. Okay, please don't panic by the calculations. Here, when you cube root 3, you get root 3 times root 3 times root 3. Root 3 times root 3 is just 3 with an extra factor of root 3 minus 3 root 3, which gives you 0. Okay, so we just found our point of intersection. It is 3, 0.
Professor, we could either plug in negative square root of negative 3, right? Or square root 3.
That's exactly what we said. Absolutely. They both give you the same point because that's what we said in the beginning. X and y are equal at those two t values. Yeah, either one. You could check. If you don't believe me, you can check. Yeah, so if I put negative root 3 here, that gives me 3 still. Okay. And if you put negative root 3 here, that would be a negative root 3 root 3 plus 3 root 3, which is still 0. Yes, you still get 3, 0 because that's what we said or what we determined. Yeah, I don't know how the book expects you to draw a curve without finding the point of the self-intersection. Often students are confused with graphs in this section. Okay, now I should mention that finding the point of self-intersection is not always easy. The algebra is just not going to work out. Remember, solving an equation, an algebraic equation, is almost impossible. Not all equations solve nicely. This one did. All right, so if any questions, guys? Again, this problem, you just got to do it over and over again, okay? And if I put such problem on the test, it's gonna worth like 30 points, a lot of points. So you want to make sure you learn. But any questions?
Professor,
Yes.
how is the cube root of 3 equal to 3 root 3?
Yeah, so cube root of 3 is cube of square root of 3 is what I meant to say. It's yeah, it's root 3 times root 3 times root 3, right?
Mhm.
And then those two root 3's multiplied out gives you 3, and you have that extra factor of root 3.
Oh, okay, got it.
Okay, or you could write it as root 3 squared times root 3, 3 root 3.
Okay, thank you.
Yeah, no problem. Any other questions?
Professor, could you go back to the beginning of the problem where you write C intersects itself?
Absolutely, yeah.
Is that just given? Is that part of the question?
The statement?
Yeah.
Yeah, this is just what I reviewed from here, from the last section. A curve is not simple if for u not equal to v, we have x of u equal to x of v and y of u equal to y of v. You could say u less than v here, doesn't matter. That's just a definition of a curve not being simple. That is a given.
And then we just put the T1 and T2 for u and v.
Yeah, yes, yeah.
And then can you quickly explain why we chose negative v first?
Yeah, for sure. We are assuming u and v are not equal. That we want to find guys, the word is different t values that give us the same point. Okay, so if you choose u equal to v, if I choose u equal to v, then that's two of the same t values. We are looking for two different t values.
Is it because like both u and v would be positive? Is that why?
Yeah, if u is equal to v, then the t values are the same, aren't they? Is that what we want? Do we want the same? We are looking for two different t values that give us the same x and same y. So again, if you choose u to be v, then those are not different. Those are same, aren't they?
Right. So is this okay. So is it safe to assume that like whenever you have like a square root of something, you take the negative of it?
For this type of question, yes.
For this type of question.
Yes, absolutely. Yeah. No, we don't want u and v to be equal, because if u and v are equal, then it's the same t value. We're not interested in that.
Okay.
That would tell you, I mean, if u is equal to v, then u is root 3 and time 1 is root 3 and time 2 is root 3. That's the same t value. Of course, it's going to give you the same position. We want to know if two different t values give us the same position here. And this is two different t values. U, whatever u is, negative, you take the negative of that, and that gives you v. And those are two different t values. All right, so let me get started on the next part of the problem, and then we'll continue the rest tomorrow. Part B.
Professor, could I just ask one more small question?
Of course you can. Yeah, absolutely.
If
What's
v,
that?
when we plug in v equals root 3,
Uh-huh.
If it didn't satisfy the u less than v, then we would have a simple curve.
Okay, I'm sorry. Let's ask that again.
So you see how, excuse me, we have for the 3 solutions we found, 2 were ignored, but the last one satisfied.
uh-huh.
If that last one was also ignored, will we then have a simple curve?
Yes, of course. Yeah. Yeah, for sure.
Thank you.
If you can't solve the equations, then you would have a simple curve. Yeah. But I mean, but again, that's not going to happen because we found those 2 solutions. We found 2 different u and v's, didn't we? We found 2 different t values, right? I mean, yeah, we found t1 and t2. I just want to know, like, which one of these, where is it? Which one of these? So you got 3 solutions. We want to know which one of them gives us the same, yeah, the same x and y. And the last one did. But yes, the answer to your question is yes. Okay, so again, guys, if you have questions, let me know. You could stop me at any time. I'm not gonna need really the second derivative here, to be honest with you. Let's just focus on the first derivatives here. So I'm gonna find dy dx only here. I'm gonna focus on that because we want to know which direction things move, okay? So to find dy dx, again, here are parametric functions. Let me just copy those down here. That's our C. So what you do is you find, again, dx dt, or you could call it x dot, that's 2t, and dy dt is 3t squared minus 3. Okay, and dy dx by chain rule is, again, dy dt over dx dt. Okay, dy dt is 3t squared minus 3 over 2t is the dx dt. So again, this gives us slope of the tangent line at any time. All right. So let me tell you what this is good for, and then we'll continue tomorrow. This is good for, guys, to see when the slope is horizontal and when the slope is vertical. That's one of the applications of dy dx. Okay, and those are important pieces of information. You want to find the points of horizontal tangency and vertical tangency. Okay, that gives us basically maximums and minimums, local max and local minimums. So if I set dy dx equal to 0, dy dx equal to 0 tells you where the tangent line is horizontal. That's like, those are critical values, aren't they? And that information can be used to better graph the curve. Okay, if I know when horizontal tangencies happen, then I know where we have like a maximum or a minimum, max or min. I can also use this formula to see where the tangent line is vertical. Vertical, you just set the denominator equal to 0. But we'll continue tomorrow.
Thank you, Professor.
Guys, have a great day.
Thank you.
Yeah, I'm gonna
Thank you,
upload
Professor.
these. No problem. I'm gonna upload these notes within the next hour. I usually wait till the end, till all my classes are over. But since I'm giving a test in the next hour, I have time to upload these. So have a good day.
Thank you, Professor.